Welcome back. All right, let's pick it up from where we left off. So now let's calculate the rotational inertia for our diatomic, right? So that's going to be m1 r1 squared, m2 r2 squared. Okay. From our previous derivation, we know that R1 is going to be equal to 1 plus M1 over M2 times R0. Remember, R0 is the diatomic distance between molecules, atoms rather. Remember what we have here. So we have M1, M2, and your book is calling this equilibrium distance between them as R0. Okay, and we have that R2 is equal to R2 is R2, if I can find it here, hang on a second. R2 is crap. Give me a second here. So R2 is gonna be no, hang on, this is not, see, this is where I got messed up. Okay, hang on a second. Let's go back here. Boop, 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 boop. All right, we'll get this right. So there we go. So so now what we have is R1 is going to be equal to M2 over M1 plus M2 times R0. Okay. And R2 is going to be M1 over M1 plus M2 times R0, okay? And those go back to the previous derivations that we had in the last session, right? So we know that R0 was equal to 1 plus M2 over M1 R2, and that R0 was 1 plus M1 over M2 times R1. Okay, so that's how we got these. Beautiful. All right, we got that squared away. So let's now calculate. Let's take these. This goes into here. This goes into here. And so now the rotational inertia is going to be then M1 times M2 over M1 plus M2 squared times R0 squared. It's going to be M2 times M1 over M1 plus M2 squared times R0 squared a little bit of algebra here now. So this is going to be m1, m2 squared, m1 plus m2 squared, r0 squared, plus m2, m1 squared, over m1 plus m2 squared, r0 squared. I'm going to take out an m2 here. This is going to be an m1 times m2 over m1 plus m2 squared. I'm going to take out an m1 here, so this will be m2 times m1 over m1 plus m2 squared. This is going to be r0 squared. This will be r0 squared. This becomes then m1 plus m2 times m1 times m2 over m1 plus m2 squared times r0 squared. Factoring those out, remembering this is the rotational inertia. Right, one of these goes with one of these, and I get m1, m2 over m1 plus m2 r0 squared. Now this comes up frequently in central force problem for two bodies, the two-body problem, and so we give some special names to this assemblage of masses. So we define 1 over mu as 1 over m1 plus 1 over m2, where mu is called the reduced mass. And so then 1 over mu is equal to m1 times m2, m1 plus m2, where that mu then is equal to m1, m2 over m1 plus m2. Okay, and so that's that. So then what we have then is that the rotational inertia is equal to the reduced mass times the atomic separation squared. And we have to recall a couple of things, right? So the rotational inertia is a physical property of the molecule. And angular momentum is a dynamical variable. Okay, and we remember from our discussion, right? So recall from our discussion of the hydrogen atom that L squared is quantized. And so you'll remember that L squared was equal to L times L plus 1 H bar squared, where L is equal to 0, 1, 2, etc. So we're gonna steal from the hydrogen atoms analysis, and this then is going to relate. This then is going to relate to the rotational angular momentum of a diatomic molecule. Okay, so we're kind of cribbing from what we got from the hydrogen atom, but at the end of the day it works, right? So the energy now for rotation which we arrived at earlier, was 2 times L squared. L squared over 2 times the rotational inertia about the center of mass, right? So this is the rotational inertia about the center of mass. And so now we can write this then as h bar squared over 2 times the rotational inertia, the center of mass, times L plus 1, where L is equal to 0, 1, 2, etc. And L now is the rotational quantum number. It's the rotational quantum number. Okay. So then if we want to look at the energy spectrum, then for L equals 0, then E naught is going to be then h bar squared over 2I about the center of mass, 0 times 0 plus 1, which is 0. E1 is going to be then h bar squared over 2 times the rotational inertia times the center of mass, about the center of mass. And this is going to be then h bar squared over I times the center of mass. Go to E2, it's going to be h bar squared over 2I center of mass. This is going to be then 2 times 2 plus 1, which is going to be 3 h bar squared over I center of mass. And you can see now that the spacings, right, the spacings between levels are not the same. Okay, so the spacings then are going to increase with the quantum number. As a matter of fact, let's look at the general formula for the energy spacing between any two adjacent levels, and so that would be E sub L minus E L minus 1. And so that would be equal to h bar squared over 2 times the rotational inertia, be L times L plus 1 minus L minus 1 times L. And so then that's going to be h bar squared over 2I. It's going to be L squared plus L minus L squared plus L. And so that's going to be equal to h bar squared over 2 times I, about the center of mass, times 2L, which is going to be equal to h bar squared times I, center of mass, times L. So the spacing between levels then, the spacing between any adjacent levels is going to be proportional to L, where L is the rotational quantum number of the higher level, right? So this is going to be the rotational quantum number of the higher level. Okay. So just to get a sense of the electromagnetic radiation that's required for absorption or the electromagnetic radiation that's emitted when rotational quantum levels are changed, let's look at this CO molecule, and let's look at the L equals 0 to the L equals 1 rotational quantum transition. And so the wavelength that's required for that is 2.6 times 10 to the negative 3 meters. which is actually 2.6 millimeters, which is 2.6 times 10 to the 6 nanometers, okay? And so if we look at that energy and get a sense for that, we will recall that energy is equal to 1240 electron volt nanometers divided by the wavelength in nanometers. So that energy then is going to be 1240 electron volt nanometers divided by 2.6 times 10 to the 6 nanometers, which gives us 477 times 10 to the negative 6 eV, or around 4 times 10 to the negative 4 eV. Now I want you to appreciate some things here, right? So in the hydrogen atom, right, electronic transitions, right, are on the order of 10 electron volts, right, and going from n equals 1 to n equals 2, right, is about 10 electron volts. So the rotational energy levels, the energy spacings thereof, are on the order of 10 to the 5 smaller, right? So these are really small energy levels, and these actually are in the microwave region. These are in the microwave region of the electromagnetic spectrum. Okay, and so again, you should have a good grounding of the electromagnetic spectrum, which we've talked about much earlier in the year. So again, I want you to look at example problem 11.1 in the text and go through that well, and we will pick it up with molecular vibrations next. Okay, awesome.